Okay, hello everyone, and welcome to our talk on using machine learning to exploit other machines. We've just had a very nice talk by Philip talking about one aspect of exploitation. We want to review a different aspect of it, and hopefully you can learn something from this talk. Usually we begin this talk, and we've done a couple of them, with this legal disclaimer, and we have to wait patiently while all of you read it. However, I no longer work for that company, so I don't have to make you do anything.
I do work. I hope that you read it all.
But I have the clicker, so I decide. So my name is Guy, and this is Ezra. We're both active, very active in the community in Israel. We both are leading the B-Sides Tel Aviv, which is going to happen next week. And if you haven't planned to arrive there yet, you should really buy your airplane tickets now. Ezra is also leading the local DEF CON community, and altogether we are doing a lot of research together for, I think, about a year and a half, 2 years now. So that's been fun. We've been around the world. Most recently, we gave a talk at the SAS conference in Singapore by Kaspersky, and in other places as well. And I will refer to some of these talks later in this deck, and I encourage you to find the videos or come and ask us questions later, because some of that can be useful for you. So to give a rough explanation of the problem, I'll hand it over to Ezra.
So the problem is like this. Imagine your classical phasing scenario where you have thousands of crashes to analyze, which is, I believe, a good problem to have. If our phaser finds crashes, our status is okay. However, having a lot of crashes means that we need to sift through them. And we can do it automatically, and if we do it automatically, we might miss some important crashes. But it helps us reduce the thousands of crashes that we have into just 100 of results, which could be interesting. I hope so. And let's also understand that if we are doing this work manually, I mean, when it gets to the actual researcher trying to find these exploitable crashes, it's not something that can really scale. It's something that takes time. It's something that requires manual work. It's not simple. So when we started thinking about this whole world, this whole set of problems, we thought that the main work that we will need to do to be able to use machine learning to help us identify these crashes, the time will be in building this particular model. And we're going to go in a few about what it's model and what it's machine learning, or at least how we believe it's machine learning and model. But when we started working with this, we identified that the actual problem was not building the model, but rather starting to gather the data that we can start using to train machines to do our work. Turns out that finding real crashes that are really exploitable, it's not a simple problem. And not only that, we don't only need to have data, but rather have good data. Because if we have 10,000 times exactly the same crash, it's not going to help us. We need diverse data. We need diverse crashes that are exploitable. So as we can imagine, as we can understand from this point, it's not simple. And one of the things that I had seen in the past that it's very useful when you are having this kind of problems where you don't even know where to start is just to define it, and define it as well as possible so you will be able to concentrate directly into what you need to solve. So having said that, we thought about how to make the question of the problem, which is, what is Australia? Anyways, now we're really talking. The problem was, can we create a machine learning model that can triage these crashes and can help us as researchers only to focus on the exploitable ones? Because again, Guy is going to tell you a little bit of the story about how we started with this, but we had a big, big, big corpus of AFL crashes.
So to give you some background, a bit of a story about how this presentation came to be, I'll give you a couple of sentences of what we previously done. So my team, and Ezra's team, my team, and the others were trying to build exploits, actually finding active exploits in machine learning stacks. So that's a whole different talk, and it's an interesting one. But we had a problem where we were fuzzing the system, running a lot of different inputs on the systems, and getting a lot of crashes, a lot of results. When I say a lot of crashes, I mean a couple of tens of thousands of crashes that we had to triage, we had to separate, we had to bring some order into them to know where do we want to invest a lot of labor into understanding if they're exploitable or not. So we were riding the car from, I think it was from San Jose, southern Bay Area, all the way to San Francisco, and we were talking, well, we need a new idea for the next conference we want to submit to. And wouldn't it be really cool if you could use machine learning to do all of the hard work for us? Because we were spending a lot of time trying to investigate those AFL results, those crashes. What if the machine learning model could do this for us? So from that car ride, that drive to San Francisco, came this talk and this idea and this project. So to define this more specifically, what we wanted to achieve was to create a machine learning model that would take what we were doing by hand, which was to run a tool called exploitable. A side note here, every time that I say exploitable and you see it underlined, I mean the tool, not the adjective or the verb. So we were using this tool, exploitable, against our inputs and trying to discern if this is a good crash or a bad crash. Good as in, is it exploitable or not? So if we can create a machine learning model that can outperform exploitable, meaning that it can work faster, or it can find more cases, or you can use it more flexibly, then we could move through orders of magnitude more crashes, at least in our vision. So the first thing that I really want to share is the full disclosure. For this project, we had a very limited data set. I'm going to explain exactly why. This is not like a deep learning project or some other kind of buzzwordy thing. What we wanted to achieve in this talk is to share the methodology more than the results, even though we will share the results. But our aspiration is that people who find machine learning either too buzzwordy or too scary to take the time and try to use machine learning for other purposes, even offensive purposes. And in the end, we're going to show you some results, and we will explain why you can't trust the results that we show you. So the first thing is, what the hell is machine learning? So a lot of people are hearing the buzzwords and treat machine learning today a bit like they treat blockchain. It's a big buzzwordy thing. It doesn't really have a lot of value, and we should really wait for the storm to pass and everything to return to normal. Well, machine learning is a buzzwordy thing. There's no argument there. However, it is a tool, and as a tool, it has its use case where it's very, very effective. And it has other use cases where obviously it isn't. What we're going to show you today, how to understand which use cases are applicable for machine learning and which use cases are probably not a good idea to use it. And they're more of a buzzwordy scene kind of thing. The other thing is that we've spent, well, I don't know, about 18 months researching the security of machine learning systems, as I said, referred to in the other talk that we gave. And machine learning systems have a lot of issues, which I'm not going to go into here now. But what they do share in common is that the way that they analyze the data and they produce the results is something that we, as security researchers, can use. We can use those systems to make our lives easier. So generally speaking, what is machine learning? Machine learning is a process. It's a process that feeds on data on one end and spits out results on the other, just like any other process, just like any function call that you use. There are some caveats, some things that you have to be cautious when you're using machine learning. But once you understand what those caveats are, it'll make your lives much, much easier. So the first part of I will try to use my pointer. I'm not sure if I can, or here it is. So the first part of the pipeline is data ingestion, the way that the machine learning model is feeding on data. Usually, when you think about machine learning models, you might have something like churns inputs like images. I'm building a machine learning model to discern between images of cats and dogs. So the inputs to that system would be images of cats and dogs. Sometimes it would be labeled images. So I'll provide an image of a cat, and I'll also provide a string, this is a cat. The machine learning model will take these inputs and will try to build an internal representation of that model that it will match against whatever it saw previously. So if I give them 1,000 images of cats, different cats, and 1,000 images of dogs, it will try to build a model that would differentiate between cats and dogs. So when I present a new image of either a cat or a dog, it will know it belongs to this class or to that class. Basically, that's what it's supposed to do. However, machine learning doesn't really understand images. Definitely not as we humans look at images, but it understands bytes. It understands data structures. So the second step here is to look at those inputs and to decide what kind of features are you going to look into when you're looking at that input. For example, if you're looking at an image, do you want to look at the ratio between pixels? Do you want to look at the color histogram? Do you want to look at the size? Do you want to look at the geometrical relationship between the objects in the image? There are a lot of different features that you can look at. But one thing that you're definitely not doing is not look, oh, it has 4 legs and it has a long snout, it's probably a horse. That's not the way the machine learning does. It's just a computer software. So once you determine the features, you run the machine learning process and you train it. I'm not going to go into it, but then you have a model. And the model is an iterative process where you feed it more information, and as it gets more information, usually it improves. Usually, and when it doesn't, you have to go back to the drawing board and try again. But in the end, we have a machine learning model. And then you get the predictions. So you put an input on one end, and you get a prediction. I think this is a cat with a likelihood of 0.76. Basically, that's what it does. So let's start with what it isn't. First of all, this is not magic. This is like basic algorithmic stuff that's known since the 60s or the 70s. There's nothing new in machine learning for the past 30, 40 years. The only thing that is new is that now we have more CPUs. Now it's scalable. It wasn't 30, 40 years ago. The second thing is that if you've ever studied in college something called linear regression, you now understand 90% of what machine learning is. The third is, it's not really difficult, it's not really complex. It is if you're trying to develop new things, new algorithms. But if you're trying to use what already exists, it's just like using a framework. If the framework exists, that's really easy to use. But if you're trying to write your own framework, you probably need to put a lot of thinking, a lot of effort into it. Unfortunately, it is one of the holy VC buzzwords, just like cyber, zero trust, and blockchain. So it does create a lot of unfortunate uncomfortableness for people when they are talking about machine learning. So this is a good rule of thumb for everyone to have. If somebody is talking to you about machine learning and it has code, that's really machine learning. And when you have slides like me, that's bullshit. Sorry, that's PowerPoint. So I'll give you an example. The title to this talk is Using Machines to Exploit Machines, Harnessing AI to Accelerate Exploitation.
So it's in PowerPoint.
Sorry. Everybody says AI. There is no AI. Sorry to do the spoiler for you. There is no artificial intelligence. Not yet. Probably not for the next 10 to 15 years, at least. There is machine learning. And everybody mixes them up. We mix them up as well. And I will mix up during the talk. However, it is a tool. And as a tool, it's very useful for some things. It's very useful for finding patterns. When you have huge amounts of data, you can educate the machine learning model on what patterns you're trying to look for much faster than you can actually write your own heuristics on all of it. It's also much easier to build models to correlate between different inputs. If you're looking at a lot of logs and you know that if someone is located at a specific country and it has a login at the same time from a different country, that's 2 pieces of information that writing heuristics for is possible, but it's painful and it usually takes a lot of time. However, you can just throw everything at the machine learning model and it will understand by itself which pieces of data is correlated and not, and which are not. But the most amazing thing, at least in my opinion, is that you can abstract a problem away in such a way, in such a sense that the machine learning model will just try to fit different variables together and spit out something that makes sense. Sometimes it does make sense, and that means that for us, we don't really need to build those heuristics. We just need to build enough information to do the feature extraction correctly, and the machine learning model will be able to actually do something with it. Predictions. In the end, the machine learning model spits out some answers. We're asking it a question, is this a cat? It will spit out an answer, yes, this is a cat, with a 76% probability. However, and this is a very strong caveat that you have to remember, it's basing its prediction on stuff that it's already seen, what it was trained on. It will not spit out answers something that it has never seen before. So if you hear someone that has like this very good machine learning model that knows how to detect 0 days, be cautious. The other thing is, it's trained on data that you supply. Just like in any other programming language, like in any other piece of software that you've ever written, garbage in, garbage out. Same thing goes for machine learning models. If you have bad data, you're going to have a bad model, which is a problem. It's not very easy to detect if your data is bad or not. So what do you get? If you build a machine learning model, you can train it to say, okay, I have this crash. Can you look at this crash, analyze it, and tell me, is this a place where I should invest more time and effort and investigate it? And if it says, yes, you should, this is a highly likelihood that it's exploitable because of reasons, then you should probably take a better look at it. But the big benefit is that if it can look at those samples and say, look, this is nothing exploitable in it, there's no need for you to look at it, I can throw out a lot of those bad results and just focus on the ones that are much more probable to be beneficials. And with that, back to Ezra.
So one of the things that we wanted to understand is now we have these crashes that are basically core dumps that happen whenever we have a problematic function in our code and on the code that we're auditing. And there are two things that before we get into details, I want to convey to you the message. The first one is that in this case, I'm only looking for one exploitable crash. I don't care if I miss 10 of them. I'm looking for one of them that it's being able to be exploitable without sifting manually through all of them. And to be able to do that, I need to understand how do I work. How, whenever I look at a crash after our long-running AFL session, I try to identify which crashes are exploitable. So to be able to do that, I model what's a common morning in my life. So actually, the morning doesn't start at the morning, it starts the night before when I left the process running for my favorite fuzzer, and I go home and I have a really good sleep. And the next morning, I wake up extremely early, around 11 o'clock in the morning, to drink my first coffee of the day, because without coffee, no life. And basically, I plug this crash dump that is generated in the crash. I open my GDB, I take a look at this particular crash, and I start to analyze a lot of stuff that it's in there. I take a look at the registers, I take a look at the backtrace, I take a look at the memory locations, and I need to do it to be able to identify what works, what doesn't work. And one of the most important things is that this is a process that a lot of experience it's behind it. I do it based on what I know. And if we remember, like Guy was explaining before, machine learning is good at solving problems it has seen in the past. So by conferring these same scenarios to the computer of how I take a look at the problem, it's possible that it will be able to outperform me. So if I were to map this process to a computer way, a machine way. Oh, and sorry, before that I forgot the most important part. Honestly, the fun part of all this is to start developing the proof of concept. I mean, going through the crashes, it's a hard process that takes a lot of time. And we want to go to the proof of concept development as fast as possible. So with machine learning, if I was able to do it with AI, AI overlords do not need sleep, so everything is faster. They also don't need coffee, which is probably the reason why we will have a machine group racing eventually if we arrive to AI. The pre-processing phase prepares the data for the machine learning analysis. So if previously I was opening every crash and I was extracting all the features, like the registers or the memory locations or the backtrace, now the computer can do it automatically and generate now this information that it will be automatically triggered into the machine learning process. And then it's being automatically analyzed based on the same experience. Like I have my experience, I train now the machine learning to have similar experience to the experience that I have. So if we were to use the phrase that Guy defined in the previous slide, is how similar it is to what it has seen in the past. And it meets its predictions based on the human intuition, or in this case, the heuristics. And it will tell me, yeah, this crash, it's certain probability to be exploitable because it's similar to what I know. And at this moment, the computer just can leave us the fun word to start developing the proof of concept.
I mentioned earlier that getting good data is a big problem. So I want to describe where we looked for and where we found our data. But before going into that, I want to clarify something and make a remark. When we're talking about finding crashes, what we mean by that is that we're trying to run some program, imagine some program running on some library that we're calling the function from, and we're iterating on different inputs. So for example, you have a command line operation called command.exe, and you try and /a equals bbb, /a equals ccc, /a equals ddd, whatever. You're running on different inputs. If one of those inputs causes the program to crash, we want to capture the information, the crash information from that crash, so we could analyze it. When we're talking about data, that's the data that we're talking about. We want to know which input caused the program to crash, and we want to know what was the state of the program at the moment that it crashed. So we need a good source of information that has these properties. And apparently that's pretty hard. Nobody's really keeping track of whenever your program crashed, it was because it was of an exploitable bug. We have a lot of crashes. There are a lot of repositories of crashes. But nobody really sat through it to say this was because of an exploitable bug, but this was not because of an exploitable bug. This was just a regular bug. So getting that kind of information is pretty hard. And that kind of stopped our research for quite a while until we stumbled upon the DARPA Cyber Grant Challenge. So this was from a couple of years ago. But what they've done in the Cyber Grant Challenge is that they've annotated that data and they gave it away to researchers during the competition for them to create machine learning models that can do some stuff with that data. So what we have here is 632 different cases, different programs that we know have exploitable crashes. How do we know? Because the data comes with a wiki. And on the wiki, it says, when you run this program with that input, you will get a buffer overflow. So we know each and every one of these 632 different crashes is exploitable. But when we ran them through the program exploitable underscore here, when we ran them through the program, it only correctly identified 607 of them as exploitable and gave 12 of them probably exploitable, and 13 of them, I have no idea what it is. And that means that our tool, our exploitable tool, we didn't write it, we just used it. When we used that tool, we left a lot of exploitable crashes somewhere lying on the floor. We couldn't identify them. So if we trained our machine learning model to actually be better than this, then we would be better than the state-of-the-art tooling that we now use in order to identify crashes. So what kind of information does a crash give us? As Ezra mentioned, it gives us registers, so we know the EAX value, we know the stack pointers, we know the destination index, etc. We know the instruction pointer where it was pointing at. We have a lot of the data that comes from the CPU and the state of the CPU at the moment of the crash. We also have other pieces of information, like what was the input, the timing, stuff like that. But we chose to focus on those registers because we thought, well, maybe they would be enough. Maybe they would be enough to correctly identify a program as a bug, or more correctly. They could better identify a bug if it's exploitable or not. So what was our process? We built a harness and ran all of those different programs through our harness and created those crashes with different inputs. And we collected that data, the crash analysis, and then we fed that data into two different forks, two different ways. The first one was running it through exploitable and recorded whatever exploitable decided that the result from that analysis was. And the other was through our model and compared the results. But we encountered a problem right out of the start. Looking at registers is very, very interesting, but the data that those registers contain is not exactly the same. Think about the EAX register. It can at one point in time hold a value like 3 or 4 or 5, but it also can find an address somewhere in kernel space, which would be hex value FF something, something, something. So if you look at this graph shows you the sparsity of the data space for those registers. So this is specifically for the ECX register, and you can see that there's a lot of low values and there's a lot of high values, but there are really very few values in between them. And high value here is a decimal above 40 billion, sorry. So that means that all of those high values that we're seeing are probably addresses, and all of the low values that we're seeing are probably, let's say, working numbers during computations. And it's not the same thing. It's not the same thing for when you're trying to analyze what the program is doing. Is ECX holding an address or is it holding a value? So we had to separate these two cases. So what we're trying to do is to build a way or teach the model a way to discern between the two cases. And we were quite unsuccessful at first. It didn't work. We didn't get good results. And then we thought about this. This is something called binning. Instead of looking at the values as a discrete value, which has like a range, we can look at the different baskets and see how many values fit into each bucket. And what we did, we took the entire range and divided it pretty uniformly to 10 different buckets. So the first bucket and the last bucket had lots of values, but let's say the buckets on the edges had more values, but the buckets in the middle had very few values because that's the way that the data behaved. And once we've done that, the machine learning model found it much easier to understand what the data is, because if it's a low value or a high value, it makes it much easier to understand if it's exploitable or not. So the first thing we've done, we tried a machine learning model or machine learning algorithm called one-class support vector machine. I'm not expecting anyone to actually recognize this, but I will give you a brief introduction what it means. So imagine that we have two classes of information. We have black dots and we have white dots. Our purpose is to find a way to separate between these two classes of information. So we can start with a green line, which we can all see is a pretty bad fit because it doesn't really separate well the two classes. So we can progress to the blue line, which does separate the classes pretty well. There's all of the white dots on one side and all of the black dots on another. But it's not very optimal because the distance between each dot and all of the other dots is not the same. It's not optimal. So if you look at the red line would say, okay, this is the minimal distance that each cluster has from each other. And that helps us to build a much better rule of thumb when trying to separate the data. So this was like a very hand-wavy explanation of what SVM is. But the bottom line is that we took this model to the data that we had and tried to train our model using this algorithm to get better classification results. And what we found was that out of those 25 records that the exploitable was not correctly identifying, we could categorize 23 records out of them as exploitable and 2 of them as probably exploitable. And we didn't leave any crash lying on the floor unidentified. So we were already performing much better than exploitable. But we didn't stop there. We tried another algorithm because we weren't sure that this algorithm was really robust enough, really strong enough for our purposes. So we took something called cosine similarity. What cosine similarity means is that we are looking at this huge multi-dimensional space, which for this example would be a two-dimensional space, and say we have two things. We have a burger and a sandwich. These are 2 points on the axis, and we are calculating the cosine angle, the cosine of the angle between them. That's a bit of math, sorry. But basically what this means, I'm trying to calculate a metric that says what is the distance between the burger and the sandwich points in my data plane. The same thing goes when I'm looking at all of the different registers. If I can look at all of the registers that belong to the exploitable class and say, okay, this new class, which I don't know what it is, what's the distance between it and all of the previous points that I already know? If it's close to them, it's inside the same cluster, it means it's exploitable. If it's far away from them, then it's not exploitable. It belongs to a different cluster, or it's an outlier. So we took this algorithm to our data, and we got interesting results. When we did the basic thing which I just explained, which is a linear cosine similarity, meaning just like the algorithm which I just explained, we were correctly identifying 16 results that the exploitable was not able to identify. However, when we use something called centroid similarity, which means we didn't look at it as a plane, but more like a sphere, when we did that kind of calculations, we did much better. We correctly identified 22 more cases, 22 more crashes that the best state-of-the-art heuristic was not able to identify, which is pretty nifty. And the last experiment that we ran is called XGBoost. XGBoost is an algorithm that tries to build out a tree that says, okay, this parameter, this variable that you're looking at is more important. It has more impact to the prediction than any other variable here. So it will start with the first variable and the second variable, et cetera, et cetera, et cetera. And then it gives you a structure that you can say, okay, this is my data, and apparently ECX is much more important than EBX for some reason. I have no idea why. But that thing I can analyze and understand what am I seeing when I'm analyzing that data. So we trained our model in the usual way that you train models. That took 80% of the data. We did the churn, we did the analysis, the validation, etc. And we got fantastic results. The worst case that we got was 95% accuracy, and the best case was 99% accuracy. And that sounds very good, very happy, but actually that's crap. Let me explain why. Assume that we had a system that would take inputs and just return the same result again and again and again. My data had 96% exploitable pieces of information in it. If I had a function that only returns exploitable for every time that it's called, it will be correct 96% of the times that I call it. It will be wrong on 4%, but that's a pretty good function there. And I don't really need machine learning in order to do all of that. I can just everything is exploitable in my world now. So that was not a very good result. So this algorithm really showed us that we had a problem in the data that we were looking at. The data was corrupt. Well, corrupt may be not the right word, but the data was biased. We didn't have enough information. Our information was not diverse enough. But it did give us something that we could use. When we looked at the tree, we could get some information out of it. For example, trying the pointer again, you can see that if EBP is in the first bin, and ESI is in the first bin, and ECX is also in the first bin, there are 16 records that match this. 7 of them are exploitable. Again, you can follow the tree, and you'll get 26 exploitable, etc. However, if you're saying, okay, EBP is not in the first bin, it's anywhere else, but not in the first bin, and ESP is not in the second bin, you would be correct 90% of the times, which I find absolutely crazy. That means we have a rule of thumb to analyze any software that says if you have a crash and your register value in EBP was not in bin 1, and the register value in ESP was not in bin 2, which means they did not have a very low value, then you have an exploitable crash. Well, to borrow a word from our friends across the pond, this is bollocks. This does not make any sense whatsoever. It does fit the data. It does fit the data in the sense that we fed information to our machine learning model the machine learning model gave us answers back. It's not lying. It just says that this is not a real-world production-ready tool because it will be wrong quite often. And it's an open question, would this still be true if you fed it more data? I don't know. So to summarize that piece, comparing our machine learning model versus the tool called exploitable, the state-of-the-art heuristic-based model, we show that on the same data, we can do much better than exploitable, which gives us a strong sense, a strong smell, that there is a way for machine learning to outperform the way that heuristics are doing today. On the other hand, we don't have enough data. We don't have enough data to say, this is a good machine learning model, go ahead, take it and use it. Otherwise, we would have released it 6 months ago. What we're trying to share here with you is that it's possible to use these kinds of tools in our world, in our offensive research world, in order to make our lives easier, to get more information, to better understand the behavior that we're trying to learn. So if you're interested in diving deeper into this world, we really recommend to read the white paper. The URL is here. You can take a photo if you want. If not, it will probably be released in the conference later. And also, check out our videos on our previous work where we also explain how you would attack this, how would you go ahead and exploit machine learning models running in production, how would you break them, how would you subvert them. But in the end, this is a call out to everyone else and saying, you can take this research, you can duplicate it, but you can extend it. You can take it into your own world and try to build upon it. And we encourage you to do it. And we would be glad to help. So in conclusion, machine learning, the bottom line is it will only answer this question. How similar is the thing that I'm looking at right now to everything that I've seen in the past? If you have questions that are a good fit to this kind of model, machine learning is the right tool for you. From a data perspective, we had a biased piece of data. We had 632 software data points that were all exploitable, which is pretty bad because we needed at least 632 software programs that we knew for a fact that were not exploitable as a control group. And without that control group, we got really bad overall results because we can't really trust what the machine learning model is telling us. So what we're trying to tell you is that machine learning can be used, it should be used, but you should be very cautious when you use it, because it's very easy to walk down a path and get some very amazing result and miss out entirely that you had like a serious mistake somewhere in the beginning. So imagine that this would be a world where the machine learning model worked. Where could you use it? Well, I always try to think of what would the blue team do with this kind of technology? What would they do with this kind of results? So imagine that you could go over all of your bugs in your bug tracker, all of your crashes that somebody found, and say to your teams, well, these are high priority because our tool says that they are exploitable. And the rest of them, magic. And the rest of them are not exploitable, so give them lower priority. That would be a high benefit to any kind of software house that's trying to solve the real issues, because you really should focus on what's exploitable before you fix everything else. It's also good for us, for vulnerability hunters, because if I can take a piece of software and take 10,000 attempts at attacking it, and just looking at the 10 that are actually exploitable, I would save a lot of time, I will get greater focus, and I would get better results. But in the end, the bottom line is that if we could integrate this into existing tooling like fuzzers, fuzzers would be able to learn and to focus much faster on high priority paths when we're exploring their fuzzing goals. And that would mean we would get better, higher quality results from those fuzzers when we're trying to find those exploits. Data science is an art, even though it has science in the name, and that would probably be true with whatever PhD you would talk to, probably not someone from marketing, but PhDs would tell you this is mainly an art. What usually happens in machine learning experiments, projects, or products is that you go back to the drawing board again and again and again and again, because it's an art, and you really have to develop a sense of what would work, what wouldn't, and run those experiments. But for us, the biggest learning from this was that we needed to take our world, the way that we look at the world as exploit developers, and talk to people in other domains with other expertise, because they have tools and they have methodologies that can help us do our job much better. So to wrap this up, we want to acknowledge Dennis from our team, but also the people behind the Cyber Grand Challenge and the people behind the wonderful exploitable tool, who we really built a lot upon their work. And with that, thank you. So we have some time for questions, and if you would submit your question into that deck, which I think we're seeing right now. Okay, starting from top to bottom. I believe what you call predictions could also be a classification. Isn't classification more relevant in exploit research than predictions? Well, prediction is an abstract way to think about classifications, while classification is only relevant to algorithms that do classifications. There are algorithms that don't do classification. So I hope that kind of answers the question. What type of machine learning are you discussing? Can I assume you're talking about unsupervised machine learning? In the sense, this is a branch of supervised machine learning because we fed it information. However, it was a single class supervised learning, as in we didn't have additional data. Before I continue to reading off the screen, any question from the audience?
Here.
Thank you, sir.
In the decision tree that you showed, you're giving are you applying Bayesian to this at all in order to have some sort of probability distribution to look at the data from another standpoint? Because with the decision tree, you end up with a fairly binary number.
So the answer to that is, like all good things, yes and no. So for that specific algorithm named XGBoost and the other variants of XGBoost, this is not the way it works, so it does not give you out probabilities. You can discern probabilities in a sense out of it, but you wouldn't count on it. There are other algorithms that actually do give you a classification tree in a sense that you can say, okay, this is a higher probability, this is lower probability, and kind of mix and match between them. We didn't do that, but we are aware of that probability. Of that option, but it leads to a much more diverse information gathering, which we didn't have. Another question from the audience? Yes, sir. So I'll say two things about that. The first one, they are openly available by the DARPA project from the US, so you can download the sources for all of them, compile and run them. We also built a harness, which was basically a Docker that compiled everything and then fed out the crashes into a different Docker that did the analysis, and we built an entire pipeline, which I didn't discuss here, but we can release it on GitHub. It's completely free. Okay. Another one from the audience, or I go back to the screen? Okay. Is exploitable open source? Yes, it is. Open for contribution. I believe it is, but you have to check with the GitHub page and license and everything to see how they do that. Is it more efficient to have multiple models for each type of binary trash dump, or only one model that's well-trained enough to be applicable to all cases? That's a good question, actually, and that comes into something we call the cascade effect. Imagine you have like a single all-knowing model that can handle all kinds of cases. That would be absolutely ideal and therefore does not exist. On the other hand, you can have a relatively good model that would be correct in 90% of the cases, and then maybe you would like to have another model that will look at the same inputs and be correct at 30% of the cases, and another model does, I don't know, 50% of the cases, and then aggregate those results and compare them and get like a cascade effect between them. Because if each model is trained differently and looks at a different portion of the picture, combining the answers, if 2 out of 3 say that this is exploitable, it's probably something that I need a human to take a look at. If all 3 decide that it's not exploitable, I can probably just chuck it aside and ignore it. Hope this helps. Another question from the audience?
You can also find us if you want to discuss.
We'll be available in the hall outside for more questions. Would this work in Australia? Yes, but you have to turn it upside down. Thank you.